In this video, we're going to learn about how to find the electric potential when we already know the electric field. To derive an expression for the electric potential from knowing the electric field, we're going to consider an arbitrary electric field represented by the lines in this figure that you see here. And we're going to say that we have a positive test charge that's moving along the path that's shown from I to F, or the initial to final location. We're going to start out by finding the work that's done. And to find the work that's done, we know that the expression for work is the integral of f dot dr. Now, we also know that this F that this particle would be experiencing is the electric force. And so we can substitute Q times E for the F. So Q times E dotted with dr. That gives us the work that's done by the electric force to move it in that direction. And we know that the work done by the electric force is the same thing as the negative change in electric potential energy. So the negative change in electric potential energy can be expressed as the integral of QE dot dr. Now, we've also learned in the past that the potential difference, or delta V, is the same thing as the change in electric potential energy of a particle divided by the charge of that particle. So let's put this all together here. The potential difference is equal to negative integral of QE dot dr divided by Q. And we know Q is a constant. And so I can pull Q out of this integral. And so it would be negative Q times the integral of E dot dr divided by Q. So my Q's cancel out, which means that the potential difference, or the change in the electric potential in this case, can be expressed as the negative integral of E dot dr. And that's our general expression that helps us find the potential difference, or the change in electric potential between two locations when we know the electric field in that specific region. Now, just a couple of further comments about that. If we want to know just the electric potential at a specific point rather than the difference, or just the potential difference, we often call that, we're going to assume that our initial point where our particle starts out is infinity. Because at infinity, the electric potential is equal to 0. So in other words, then my final electric potential would be equal to my change in electric potential. A couple of other comments here. That if we happen to have an electric field that is constant as well as parallel to the way that we move our particle, then quite often we use the expression B equals E delta x, where delta x represents the displacement of our object. Lastly, thinking a little bit about units here, quite often when we're dealing with electric potential, instead of using the units of newtons per coulomb for an electric field, we'll use the units of volts per meter. A volt per meter happens to be the exact same thing as a newton per coulomb. So let's take a look at a couple example problems that'll help us use this concept. Our first one is problem 7 in your textbook. It tells us the electric field. Specifically, we know that the electric field has an x component, and its y and z components are 0. So if I wanted to express this electric field in rotation, I could express this as 0.00 newtons per coulomb times x by that. And then we have a particle that is moving from point A on the y-axis at y equals 3 meters to point B, which is on the x-axis at x equals 4 meters. So to be able to find the potential difference between B and A, we're going to need to express this displacement of our particle as a unit vector. So I'll call that R. And our object starts off at the location y equals 3 meters and goes to the location x equals 4 meters. And we know that when we're doing a displacement R, we are looking for final minus initial. I could express this as 4.00 meters I hat minus 3.00 meters j hat. Now, this is not a constant electric field, which means I do have to use an integral. So we know that delta V, what we're looking for, is equal to the negative integral of E dot dr. And plugging in what we know here, we know that our object is moving, or actually, let's just do this. Let's take care of the dot product first. So I have E dot dr. Now I used a delta R here. In this case, they are nearly interchangeable. And you'll see what I mean here in a second. So let's think about the dot product for a second. When we have things that are in unit vector notation, unit vector notation, that means that when I do the dot product, I multiply the I hat times the I hat, and then I multiply the j hat times the j hat, and I multiply the k hat times the k hat. But notice that my electric field vector doesn't have a j hat or k hat. Those components are 0. So really, the only thing that I care about here is the x component of my displacement. So let's plug in that electric field. 4 newtons per coulomb times x. When I dot that with dr, I end up just getting dx. Now when I think about my limits, that x component is going to vary from x equals 0 to x equals 4 meters. Right? Okay. So we go ahead and take that integral. The integral of 4x is 2.00 newtons per coulomb x squared. I have a negative sign out front, and I evaluate that between 0 and 4 meters. When I plug in my limits, I find that this potential difference as we go from B to A, and again, we're going from B to A, and that's why we have from 0 to 4 meters as my limits, is negative 32 volts. So again, as we're thinking about order of operations, we want to think about that dot product before we think about actually taking the integral. Because I have a dot product in there, I only plugged in the x component of the electric field, and then my dr became a dx. And my displacement vector, as you see that I drew here, that really helps us decide on what limits to put on my integral. Okay, so here's another problem using these same concepts. This time, it's problem 8 in your textbook. I don't want you to actually do the problem, but rather, I'd like for you to think about how you would solve the problem if you were to actually solve it. Now, if you'd like to go further and actually do the problem, you are welcome to, but it's more important to me that you understand how to solve this problem with the information given to you. This problem gives us an x component of the electric field in a certain region of space, and it tells us y and z components are 0. And we're looking to find electric potential at a couple different locations, as well as the greatest positive value of the electric potential based on this graph for the electric field. Again, plan out how you would solve this problem and bring your answer to class with you.